My name is Patrick Roberto, and I am a master's student in biology studying under Dr. Fabricio Medina-Bolivar. The topic of my presentation is over antioxidants produced naturally in peanut. Antioxidants are immensely important for human health because they prevent the overproduction of free radicals. Free radicals are highly unstable molecules that are linked to inflammation, cancer, heart disease, and neurodegeneration. Therefore, it is recommended to consume a variety of fruits and vegetables that are rich with antioxidants. Interestingly, in peanut, there is a group of antioxidant compounds known as the prenylated stilbenoids that exhibit a chemical modification known as a prenyl unit that may enhance their antioxidant capacity in a cellular environment compared to non-prenylated stilbenoids. In nature, peanut produces the prenylated stilbenoids when they are stressed by the environment. In the lab, it is also possible to stress peanut to produce a high yield of the prenylated stilbenoids using chemical elicitors methyljasminate, cyclodextrin, magnesium chloride, and hydrogen peroxide. By adding these compounds into the culture medium of peanut hairy roots, the hairy roots will secrete the prenylated stilbenoids into the culture medium. The culture medium can then be extracted using organic solvents, and the phytochemical and antioxidant profile can be determined by high-performance liquid chromatography, which separates the compounds based on their polarity. In this example, peanut hairy roots were incubated with the aforementioned elicitors for 210 hours, and resveratrol, arachidin-1, and arachidin-3 were secreted into the culture medium. These three compounds are tremendously antioxidant. And the hypothesis is that an extract that is enriched with several different compounds, including the prenylated stilbenoids, is highly antioxidant in a cellular environment. And to test this hypothesis, it was necessary to develop a cellular antioxidant activity assay based on DCFH-DA staining of Hela cells. Hela cells are cancer cells, and they were selected due to their rapid growth. DCFH-DA is capable of crossing the cell membrane where it is rapidly metabolized by the cells, and they are oxidized by free radicals to yield DCF, which is a highly fluorescent product. Therefore, an increase in fluorescence corresponds to an increase in free radical levels. And to test the antioxidant capacity of the extracts in a cellular environment, the following procedure was carefully standardized, and it included seeding 60,000 cells per well and then incubating those cells for 12 hours to 24 hours. After washing the cells carefully with PBS, they were co-treated with 25 micromolar DCFH-DA and the samples at varying concentrations for 1 hour. Then the solution was replaced with hydrogen peroxide for 1 hour, and the fluorescence was measured. And what we found was that treatment of the cells with 100 micromolar hydrogen peroxide resulted in a significant increase in the fluorescence. Co-treatment with 28.5 micrograms per milliliter through 228 micrograms per milliliter produced a significant decrease in the fluorescence, which suggests a significant decrease in free radical levels, which means the extract is highly antioxidant in a cellular environment. To further validate the conclusions of this antioxidant assay, it is necessary to perform cytotoxicity assays to determine if the compounds in the extract are toxic, and then follow up with potential in vivo studies to evaluate their antioxidant activity. And this research would not be possible if it hadn't been for the tremendous support of my advisor and my lab members. And I would also like to thank the Create AState organizers for their tremendous work to get this information available to the AState community. Thank you very much.